Hi everyone. In today's video we're going to do a mini lecture on the mechanical concepts of energy. This is some fairly important subject matter as it's going to form the foundation for our concept of energy throughout the rest of the class. Let's start with a simple moving particle along a path. And so we've got some path in an XY coordinate frame with a particle moving along on it. The particle has some velocity vector v, and acting on it are two forces, a force along the path and a force normal to the path. The force along the path changes the speed of the particle, and the normal force changes the direction. We measure the distance traveled along the path using the value of s, and in general, the force on the particle can vary as we move along the path. Let's define some state 1 with a velocity 1 and a position s1, and some state 2 with velocity 2 and position s2. Isaac Newton tells us that the force is equal to the mass times the acceleration, or the derivative of velocity with respect to time. Applying the chain rule of calculus, we can break up the derivative into dv ds times ds dt. And we can see there that the derivative of s with respect to time is just the velocity. Substituting in, we see that now we have mass times velocity times dv ds is equal to the force. This is a simple differential equation, and we can integrate it after we separate the variables to either side. And so we have f ds is equal to mv dv. We should note that the force is the force component along the path direction fs. We can integrate the left-hand side from s1 to s2, and the right-hand side from v1 to v2. Integrating the right-hand side, we see that we get 1/2 times the mass times the velocity squared, evaluated at the two velocities of our states. And so that becomes a difference in velocity squared. And here we've run into our first concept of energy, which we call kinetic energy. Kinetic energy is defined as 1/2 mass times velocity squared. On the left-hand side, the integral of the force times the distance we call work. And what work is it's the energy input required to change the kinetic energy. And so we see that the work is equal to the change in kinetic energy, 1/2 m change in v squared. And from above, we have that the work is equal to the integral of the force along the path. For a constant force, the force comes out of the integral, and we're left with just the integral of ds, and so we're left with the force times distance, which is a familiar concept from any dynamics class. Important note is that kinetic energy is a property for the body as a whole. It's a property because you don't require any history knowledge. We can evaluate the kinetic energy at any state using only values at that state. It's also an extensive property that applies to the body as a whole. By comparison, work is not a property because it depends on the process, and so we have to know the history. What work is it's an interaction that changes the energy of our system. The dimensions of this work integral are force times length. In the SI system, we use the joule, which is a Newton meter. And in the English system, we use feet times pound force, or BTUs, where a BTU is 778 foot-pounds force. Let's do another example now where we move a mass in a gravity field. So we have a mass, its weight is acting down on it, and we apply some force upward that moves it to a separate location. So we have state 2 and state 1, and corresponding location, z2 and z1. From above, we have that the work is equal to the change in the kinetic energy of our mass, and that is equal to the integral of the force over the distance. Note now that the force is actually two different components, and we need the net force. And so that force in the z direction is equal to our force upward minus the weight, which is the mass times the acceleration due to gravity. When we sub that into the integral, we can split it into two separate integrals. The mass and the acceleration due to gravity are constant, so the integral that has the weight in it can be evaluated. What we're left with is the integral of the force that we apply minus the mass times the acceleration due to gravity times the change in height. Subbing this all in and rearranging a bit, we basically end up with the change in kinetic energy plus this new term, mass times the acceleration due to gravity times the change in height, is equal to the work of our force, which is the force integrated over the distance that we move in the z direction. And here we've stumbled upon the second form of energy that we're going to encounter, which is potential energy. This is the potential energy associated with gravity. We write that the potential energy is the mass times the acceleration due to gravity times the elevation z. So now what we see is that we have the change in kinetic energy plus the change in potential energy is equal to our work. And so in this system, work is the energy input required to change the kinetic energy and the potential energy of our system. Let's do an example that applies this concept. Say we have a hill that's 100 feet high and we put a ball on it. And we roll the ball down to the bottom of the hill. We're not going to have any work in this problem. In other words, we're not going to apply any external force. Let's start with an initial velocity of 0, and our height at state 1 is 100 feet. We want to find the velocity at the bottom of the hill where the height is 0. From above, we have that the work is equal to the change in kinetic energy plus the change in potential energy. We start from 0, we end at a height of 0, and there's no work. After canceling those, we see that the mass also cancels, so the answer is independent of the mass. After we rearrange the algebra, we see that the velocity is equal to the square root of 2 times the acceleration due to gravity times the elevation z1. Let's say that this is at sea level where the acceleration due to gravity is 32.2 feet per second squared. And once again, we have our height of 100 feet. You see that the units underneath there are going to be feet squared per second squared, and when we take the square root, we're left with 80 feet per second. Let's convert this to miles per hour. 1 mile is 5,280 feet, and an hour is 3,600 seconds. You see that the feet cancel and the seconds cancel, and we're left with an answer in miles per hour of about 55 miles per hour. Let's look now at the work that it takes to accelerate a car to 60 miles an hour. Let's say we have a small car like a Miata, mass of about 2,000 pounds, and that it's on a level road. Once again, we write our equation from above that says the work is equal to the change in kinetic energy plus the change in potential energy. However, there's no change in potential energy because the road is level. In addition, we started from rest, and so V1 is 0. What we're left with now is that the work is equal to 1/2 times the mass of 2,000 pounds times the velocity that we're ending at, which is 60 miles per hour, and we're going to square it. Let's go ahead and convert that to feet per second so that we end up with better units. So once again, an hour is 3,600 seconds, a mile is 5,280 feet, and the entire quantity is squared. You see that the miles cancel and the hours cancel, and so we're going to be left with feet and seconds inside of there. We come up with an answer that says it's 7,744,000 pound mass feet squared per second squared. But we can see that there's a pound force hiding in there. Remember, a pound force is 32.174 pound mass feet per second squared. So one of the feet cancels, the seconds cancel, and the pounds mass cancel. And we're left with 240,691 foot-pounds force. And that's the work that it took to accelerate that car. Now let's take a minute and look at power, which is the rate of energy transfer by work. Any rate is a derivative in time, and so we take the derivative of our work with respect to time. Notice here that I used a del instead of a d. That represents an inexact differential. The reason the differential is inexact is that the value is path dependent. By comparison, an exact differential is represented by a d, and its value only depends on the end states. And so it doesn't matter what the path is. Turns out that all of our properties, because they only depend on the given state, get exact differentials, but things like work and other interactions will have inexact differentials. An example of a property that gets an exact differential would be position, which we take derivative with respect to time to get the velocity. And you see there that it's a definite derivative. So repeating what we have that the rate of work is equal to the derivative of the work with respect to time. So we can multiply over the dt, and we're left with dw is equal to w dot dt. And if we integrate both sides, we see now that we have the work on the left-hand side plus the rate of work, or the power, times some time, delta t. Notice here that I'm using a constant work. In general, that work can vary and you'd need a function of time to describe that w dot. But for a constant work, we can see now that the power is simply equal to the overall work of the process divided by the time that it took to do the work. So let's go back and look at our car again now and see what it takes to accelerate it at two different rates. So there's the work that went in, and now we're dividing by our time. Let's say we go 0 to 60 in 10 seconds. And for comparison, let's do the same work for the same acceleration in 4 seconds. On the left, we now have 24,000 foot-pound force per second, and on the right, we have 60,000 foot-pound force per second. We can convert this to a power. A standard unit used in English system is the horsepower, which is defined as 550 foot-pounds force per second. And so we put that conversion factor on both sides, and we see that the units will cancel out. To accelerate in 10 seconds, we need about 44 horsepower, and to accelerate in 4 seconds from 0 to 60, we need about 109 horsepower. So what we see here is that the power required to accelerate depends on the time that we accelerate over. By comparison, the work that it took to do it does not. These are going to be important concepts that we're going to run into a bunch in this class. That concludes this mini lecture. Thanks for tuning in and have a great day.